Okay, so our session is being recorded, and what we do in linear algebra is we work with systems of linear equations, and we try to solve a system of linear equations. And what I've done here in this little introductory example, let me just see here, let me make this a little bit bigger here. So you have here a system of equations, two variables, two equations, and you want to solve the system. Now, when you were back in high school, you learned one approach was the substitution method. But you learned another approach is the addition subtraction method. How many recall the addition subtraction method, that terminology? Okay. All right, good. Thank you. It's ringing a bell. It's ringing a bell. Wonderful. All right. So what I'm going to do, thank you, everybody. What I'm going to do is I want you to look on the left side here. And I have x plus 2y equals 1. And the second equation is negative 3x plus y equals 4. So what I want to do is I want to eliminate the terms with the x variable. So what I did was I said, okay, x plus 2y equals 1 is the same equation as 3x plus 6y equals 3. Oh, why is that true? Who can tell me why is that true? X plus 2y equals 1. Why is that the same equation as 3x plus 6y equals 3? That's right. We multiplied everything by 3. Thank you. Thank you. So now why did I choose 3? That's right. Why did I multiply the first equation by 3? Why didn't I multiply the first equation through by 4? Okay, that's right, Hung. That's right, Catherine. Because I want to cancel out my x terms. That's right, Natalie. And so I end up, that's right, Eleni, I end up with a 3x here and a negative 3. And I already have a negative 3x in the second equation. So now what I'm going to do is I'm going to add these two equations. I'm going to add them. Okay. And if I add, so I'm going to add the first equation to the second equation. So here's the first equation. Okay, and I added it to the second equation. I added it to the second equation here. And when I do that, I'm going to get 0x plus 7y equals 7. And you see, this is how I reduce the system down. So to do this reduction of the system, I mean, can we solve for one of the variables now at this stage? Can we solve for one of the variables? Did that help us? Sure, absolutely. Y equals 1 based on the second equation. Okay, so what we did here were what are called row operations. We did row operations. Now, well, first, are there any questions so far? Okay, all right. Well, now, what we can do is we can represent our systems of equations on the left here by matrices. And actually, on the right, we have what are called augmented matrices. So sometimes an augmented matrix is written as a matrix with dashes to separate the coefficient terms from the numbers on the right. How many maybe have seen an augmented matrix written this way? Augmented matrix. I'll write it. Andres has seen it in differential equations, absolutely. Okay, Ben has as well. So this is called an augmented matrix. Abigail is aware of it. In linear algebra, the way in the context of the way that our book is, they don't put these dashes in. You're welcome to when you show your work, like for tests and things like that. But we understand that, you know, we're taking this system of equations and representing it as this matrix, and it's an augmented matrix. And you can see the 1 and the 2 here correspond to x and y coefficients on the first equation, and the -3 and the 1 correspond to x and y coefficients on the second equation. And then you have the 1 and the 4 on the right. Now, the row operations that we did with the equations on the left, we can do those row operations, elementary row operations, using matrices. We don't have to carry around the variables. We can just focus on the numbers, the coefficients of the variables, and the numbers on the right. So look what I did here now. Going from the first matrix to the second matrix, I took 3 times the first row, that's row sub 1, which is 3 times the first equation, and then I replaced the first equation with 3 times the first equation. So 3 times row 1 replaces row 1, and then I got the 3, 6, and 3 here. And then the second equation I left alone. Okay, and then this is how you denote your row operation that you did. And then what did I do next? I took the first equation and the second equation, added them together, and replaced the second equation with the sum. In other words, I added row 1 and row 2 of the matrix, and then replaced row 2 with the sum of row 1 and row 2. And that got me this augmented matrix here. All right, so are there any questions about that? And I didn't finish up the problem. I mean, we don't have a solution yet. We know y equals 1. Well, if y equals 1, we would figure out that x is going to equal -1. But I'm just trying to show you that you've solved systems of equations before, but now you're going to solve the systems of equations using matrices and row operations. Okay. All right, and so now why, you might wonder, well, why do we need to use matrices? Well, you know, it isn't too hard when we have 2 equations and 2 unknowns, but what if we had 10 equations and 10 unknowns? You know, or even 3 equations and 3 unknowns. It gets to be kind of a headache to carry around all the variables. Okay, and we know that what the columns stand for in the matrix. So, all right, are there any questions before we get to our first? This is like an introductory example, but I want to, of course, get to some new examples. Are there any questions at all? Before we move on? All right, thank you, Nafani. All right, well then, let me go ahead. Let's actually do let's actually solve a system of equations where we use row operations and completely finish the problem. Okay, so that being said, okay, here's an example. Okay, take a moment to copy this example down. Okay, so I always try to give students time to copy examples. How many find that it's helpful to copy examples down? That writing is thinking. Okay, Natalie does, Justin, Eleanor, Lewis. Wow, a lot of you. Wonderful, wonderful. Hold on here, let me open up that. Catherine and Ariana and Olivia and Eleni and Lewis. Yeah, I mean, so, okay. Well, all right. What we want to do is we want to take our system here and write it as an augmented matrix. And you notice that instead of like X and Y, or well, X, Y, and Z, like in Math 280, if you take multivariable calculus, which I also teach, by the way, teaching that tomorrow, they use X, Y, and Z. But in linear, multivariable calculus is limited basically to 3 dimensions. So you have 3 variables. I want to be a little careful what I say. I want to be careful how I say things, but you're working in three dimensions in multivariable calculus. So, X, Y, and Z are natural variables. You have an x-axis, a y-axis, and a z-axis. But with linear algebra, you can have more than 3 variables. You can have 100 variables. So instead of using X, Y, and Z, we only have 26 letters in the alphabet. Instead of X, Y, and Z, we use like X1, X2, X3, X4, X5, X6, and so forth. Okay, so let's go ahead and proceed here. Okay, so first thing is to write the system of equations as an augmented matrix. And that's what we have here. Okay, so okay, so we could, we have 3 variables here. We have x1, x2, and x3. And we could decide to, to solve for one of the variables, we have to eliminate the other two, right? We have to reduce the other two. So it seems natural. It seems, well, what I'm trying to say is the way we're going to do the row operations is we're going to have what's called a forward phase and a backward phase. Right now, what we're going to do is a forward phase. And the goal is here, I have a column, and I want to have 2 zeros in that first column. So like I have a negative 4x1. I have a 0x1. I have a 1x1. But I just want, I want 2 zeros in that column. And I'm going to have to use one of the numbers here in the first column to help me. So what's the easiest number in the column? The easiest number to work with is this 1 here from the third equation. So what I'm going to do is I'm going to do a row swap. Okay, that's an elementary row operation. So or a row interchange, I should say. This means here I'm going to interchange row 1 with row 3, meaning I'm going to interchange the first and third equations, so that the third equation is now at the top. Okay, and the first equation is now from here is now at the bottom. So all I did was I did what's called a row interchange. All right, so far so good. Are there any questions? All right, all right. Well, now what we need to do is this negative 4 here. What do we want the negative 4 to turn into? What do we want that term to become? Good, Abigail. We want it to be a 0. So we're going to use the 1 here to help us. What do we have to multiply this first equation by in order to do what we want to do here? That's right, a 4. That's right. Very good, Abigail. Very good, Elaine. So look here at the next step. Look here at the next step. What did we do? We took the first row, or the first equation, multiplied it by 4, added it to the third row, or third equation, and now my third equation is 4 times row 1 plus row 3. So 4 times 1 is 4. Let me just hold on here. So we're right here now. 4 times 1 is 4, and 4 and negative 4 make 0. 4 times negative 2 is negative 8. Negative 8 and 5 make negative 3. 4 times 1 is 4. 4 plus 9 make 13. And then 4 times 0 plus negative 9, well, that's just negative 9. Okay. Okay, so that is a row operation. And incidentally, the number 1 here, that we use to produce the 0 here, we call that 1 a pivot. So some of the terminology that you're hearing here is actually from section 1.2 as well. Okay, but the 1 is a pivot. Okay, so the reason I swapped or interchanged row 1 with row 3 on this first step was so that I would have my pivot at the top. And then I can take a multiple of the pivot. Well, it's the first equation, but we know that a multiple 4 times that pivot 1 is equal to 4, and adding it to -4 is easy. Okay, so 1 is a very convenient pivot to use. And traditionally, when we do row operations, when we do our row operations, we like to use, when we work them out by hand, we like to use small numbers in a column as our pivot. But actually, you'll learn that a computer actually will use the largest number in a column as a pivot. The computer, like MATLAB, for instance, will use, computer software will use the largest number in a column as a pivot. And that's what's called partial pivoting. But you're not going to see, we're not going to, worry about that now. But they make a comment on it in section 1.2, numerical note on page 17 at the bottom. But let's not get too distracted here. Let's continue on here. Okay, so now the first column is as clean as it can be. We're done with the first column. But now the second column, I have this -3 here. What do I want to be there where the -3 is? What number do I want there to be there? Good, a 0. We want a 0 to be there. So what we're going to do is we're going to take, well, I have a 2 here in the second row or second equation. That corresponds to a 2 times x2. I'm going to take, I know that if I take 3 times 2, and I take 2 times -3, I'll get 6 and -6. So I'm going to take 3 times the second equation. I'm going to take 2 times the third equation, add them together, and then that will be my new equation, my new third equation. Okay, so that produces then a 0 where I wanted the 0 to be. And 3 times -8 is -24. 2 times 13 is 26. -24 and 26 make 2. Also, 3 times 8 is 24. And 2 times -9 is 18. 24 and -18 make 6. Okay, are there any questions so far? All right. Well, this is what's called triangular form, or what's known as echelon form. And section 1.2 mentions echelon form. It's a definition, but basically what you're doing is, if you look here on the bottom left part of the matrix, that's maybe, hold on, I can do a little better than that. Hold on. Dr. Duty knows a few things. You see you have a triangle of zeros here on the bottom left corner of the augmented matrix. That's why we say that this matrix now is in triangular form or echelon form. And how can you solve the system now? Well, certainly you could solve the system. You know, in the beginning, the system of equations, you didn't know, have any idea. But what at this point here, you know, when we're right here, what variable can we solve for right here? What variable? X1, X2, or X3? Good. Good. X3. Very good, Benjamin, Natalie, and Lewis. And you know, I will I don't always name names for responses, but you know that I can see your name. So definitely, because the bottom equation, this bottom equation here, I mean, this bottom equation here reads 2x3 equals 6. Well, it reads really 0 times x1 plus 0 times x2 plus 2x3 equals 6. But hence 2x3 equals 6. So x3 is equal to 2. And now you can take that variable x3 equals 2 and you can back substitute it. You can back substitute that in the second equation and solve for x2. And then you'll have x2 and x3, and you can back substitute those in the first equation to solve for x1. Okay? And that's okay to do that. But would there be anything wrong with just continue to do more row operations to break the augmented matrix down more, so that, you know, maybe in the end we could just identify the values of all the variables? There would be nothing wrong with that, right? But what we have to do now is we have to work backwards. Okay, we worked basically downwards, getting this triangle here on the bottom left, right? We work downwards. Okay, well, now what we want to do, let me just hold on here. Let me just one moment here. Okay, here's this triangle here, right? Well, could you picture us getting another triangle of zeros here? What if we were to get another triangle of zeros there? Would that be great? How many would like that?
You can solve for x1 and yeah, you can solve for x1.
That's right. That's right. Well, and Shravani, if we could get zeros in this red triangle, if these numbers, the -2, the 1, and -8, could be, if we could have zeros in those spots, then all we would need to do is just read off the values of the variables. So this is what's called the backward phase of our row reduction algorithm. Okay, and so let's go ahead. I'm gonna go ahead and this augmented matrix now, I'm going to rewrite it, and I'm going to work backwards. So let me go to the next page here. And I have it in pencil now. So we're going from, you know, I don't, you know, my goal is to help you understand things. And, you know, I don't worry about work I do being in pencil because I work the problems out just like you do. And here we go. So here's the augmented matrix. Now, what do we want -8 and 1 to be? What do we want? What do we want those spots again? What numbers?
0.
That's right. That's right. Hey, and what are we going to use to help us get zeros in that spot? Who can maybe circle? I'll change to blue here. Who can circle the pivot that we would use to get zeros in these two spots? What's the pivot that we would use? Does anybody want to volunteer? And I think you're able to write. Okay, good, good. That's exactly right. Thank you. I don't know who did that, but thank you. That's absolutely right. 2 would be our pivot. But look at this third row. Look at this third row here. You know, again, I can scale the third row. The third row reads 2 times x3 equals 6, right? So why not take the third equation, multiply it by, hold on here, one moment. I think I have a typo here. This shouldn't be a third. What am I doing? I'm not taking the third equation and multiplying it by a third. I'm taking the third equation and multiplying it by a half. That's right. So let me put a half here. Good. Okay, so I'm taking the third equation, multiplying it by half, and then replacing that, the third equation with that result. And so you get 1 and 3. You get x3 equal, well, yeah, here now you have x3 equals 6. And so the 1 is going to be my pivot. The 1 is going to be my pivot. It's a better pivot than 2 because you can very naturally figure out what you need to do. Okay, so to get a 0 where the -8 is, what am I going to take what do I multiply the third equation by to get a 0 here? That's right, Nafoni, an 8. That's right, Eleanor. And to get a 0 where this 1 is, what do I multiply the third equation by? A -1. Always the opposite. Always the opposite. Right? That's why we like the 1 as a pivot. And so I do those row operations. I do those row operations here. And then this is the resulting matrix, augmented matrix. And incidentally, these little signs on the left, these little tildes, they're called tildes. What that means is this system of equations is equivalent to that system of equations. It just means the systems of equations are equivalent. The augmented matrices are equivalent. That's what the little tilde sign means. And it's important that you adopt that notation. and it's important that that you accustom yourself while you're learning these row operations to write down your row operations. On your first exam, I am going to want to see work for the problems that you do, and that's part of your work. Now, I didn't explain how these numbers got here, but are we okay with everything in this matrix? Let me know if there's any number you don't understand. Just let me know. Okay, all right, so the first column looks good, right? First column looks good. Third column looks good. What about the second column? Not good yet. Benjamin says not good yet. Okay, well, where do we want the 0 to, okay, Haley says we need a 0 where there's a -2. That's exactly right, Haley. And so I'm going to use this 2 here as a pivot. But keep in mind, what's the nicest pivot we can have? What's the nicest pivot to use? What number is that very nice pivot? A 1. That's right, Abigail. So I'm going to take the second row, scale it by half, and replace the second row with that result. So I'm just, it's like dividing the second equation by 2. So these are, you're learning all the elementary row operations that you can do here on a matrix. Now the second equation, or the second row, becomes x2 equals 16, and now I'm ready to use this 1 as a pivot. And so I know, well, I have to go to the next page, but I won't go yet. I want to make sure I'm pacing myself right. I like to just take not rush things. Make sure everybody's comfortable. This is exactly how I would do it if I were in a class. I mean, I'd be writing on the board, and I tend to like to, well, I like to use how many find it helpful, the little pencil where I'm circling things and marking things? Is that helping? Is that a helpful thing to do? Okay, Benjamin likes it, Abigail likes it, wonderful. Okay, Peter, wonderful. Just like I would do in a face-to-face class. Okay, so now we got one more row operation left. We're going to take the second equation, multiply it by 2, add that to the first equation, and then replace the first equation with that result. May I move to the next page? Are we okay? All right, very good. All right, there's the final row operation. And now the system is what's called reduced, it's in reduced echelon form. Reduced echelon form. We can't do any better. We've reduced the system the most it can be reduced. And actually now, based on this augmented matrix here, we can just read off the solution. So what I've done is I've written now the augmented matrix back as a system of equations. I've just rewrote it. So that you could really see what's going on, really understand what's going on. And so now you have your solution. Now you have your solution. X1 equals 29. X2 equals 16. And X3 equals 3. So what does this point represent? What does this coordinate represent? Well, when we solve a system of equations, we're looking for, that's right, it's a point of intersection. That's right, Shravani. We have a point of intersection. But we're not looking at the intersection of two lines. Okay, if we were looking at, well, I want to be a little bit careful. The original, the system of equations we started with, had three variables. So let me just go back here. I'll come back, one moment. This system of equations, each equation represents what in three-dimensional space? Each one of these equations represents what figure in three-dimensional space? Planes. Good. We have three planes. Very good, Benjamin. Very good, Shravani. And the three planes, turns out they intersect in a point. And that's your solution. That's your solution. And by the way, this system of equations is what's called a consistent system. A consistent system of equations has a solution. Okay, when a system of equations has a solution, we call the system a consistent system. All right, one moment. Okay, so we work we start off working with small systems of equations because, like for instance, if we have a system of equations, in three variables, we understand the equations represent planes, and we can geometrically get a feel for what we're doing for the linear algebra involved. We can get a geometric feel of what our solution means, and that's why we work with small systems. Let me ask you: is it guaranteed that three planes are going to intersect in a point? Yeah, Justin says no, and that's absolutely true. You could have three, for instance, parallel planes. Okay, you could have three parallel planes. That's an example of a system of equations that you would have no solution. That would mean the system of equations is inconsistent. And what I want to do is I want to go to example 3 in the textbook. So let me now move on here. So I like to, kind of vary things. I try to find the best examples I can find. And so sometimes I'll bounce around between my examples and book examples, and that's okay. I do what I need to do to help you understand it. Let me just see here. So what I'm bringing up here is a electronic copy of the textbook. Can everybody see this okay? Example 3, maybe give me a few thumbs up. Okay, Eleanor sees it, good. So I know everything's working, thank you. So here, in this problem, thank you, Nafoni, we want to see, we want to see if hold on here, let me use my little thing here. Hold on. Yeah, we want to determine if the following system, if this system is consistent. And this system represents it's three planes in three-dimensional space where you have an x1 axis, an x2 axis, and an x3 axis. Okay, so now you don't need to copy this down. This is in your ebook. But let's just look at what they're doing. So first of all, they write down the augmented matrix. There it is. And in the first column, okay, they want to pick the smallest number as the pivot. So what they do is they interchange rows 1 and 2. The idea being that the 2 then is at the top. So in the first column, you want your pivot to be at the top. All right, well, we want to use the 2 to help us eliminate the 4. Now, we could, in the first row here, we could divide, or we could, well, I want to be a little bit careful here, hold on. We could, to produce a 1 where the 2 is there, we could multiply through the first equation, first row, by a half. But that's going to introduce fractions. That's okay, but look, it's no big deal to take -2 times row 1 and add it to row 3. Okay, it's no big deal to do that. And if we do that, we're going to end up with this augmented matrix here. Okay, so just kind of let me know if you have any questions. Are there any numbers that you don't understand how they got those numbers in this augmented matrix? Please let me know. if you're having trouble. The only dumb question's the one never asked. So okay, all right. Well, now at this stage, let me just hold on here. Yeah. At this stage, we want the -2 to be 0. Okay, so I'm going to use the one above it as a pivot, and I'm going to take 2 times the second row and add it to the third row. And by doing that, I wind up with this matrix here. Okay, I wind up with this matrix here where they have the 7. Now, can you tell, based on this augmented matrix here, okay, can you tell at this point whether or not the system of equations is consistent or inconsistent? In other words, we could continue, and I know there are a few responses there, one moment. We could continue to try to reduce this augmented matrix. We could, like, get a 0 in that spot, right? We could get, I'll be a little bit careful here. We could get a 0 in this spot. We could do that, but is it worth doing? And the answer is no. Let me see, there were a few chats here. So, all right, well, let me ask you, is this system here consistent or inconsistent? Okay, and all answers are welcome. All right, so I always like it when we have a difference of opinion. Some people think consistent, some inconsistent. Okay, so, all right, it's going to be inconsistent. Which row is the problem? The first row, the second row, or the third row? Okay, good. The third row. The third row is the problem. The third row is the problem. Now, why is that? Let's look at the third row. Hold on here. Who can chat out what the third row, what the equation is corresponding to the third row? Who could chat it out in the window? Oh, all right. Catherine says you can't have 0 times x1 plus 0 times x2 plus 0 times x3 equals 15. That's right, because we ended up with that. I want to be careful. We ended up with that, but the question is there an is there an x1, x2, x3? Is there a value for x1, x2, and x3? Or I want to be careful. Are there values for x1, x2, and x3 that would satisfy the third equation? No. Because 0 times x1 plus 0 times x2 plus 0 times x3 can never equal 15, no matter what x1 and x2 and x3 are. So basically, we got the system in triangular form, in lower triangular form, we'll call it. This is the corresponding augmented matrix. And like you said, there's no solution to that. There's no value for x1, x2, and x3 that would satisfy the third equation. And so the system is inconsistent. We have an inconsistent system. And incidentally, on the left here, they have a little picture of a possible inconsistent. Well, they have a picture of the inconsistent system. They have, in that figure, they have they've drawn the planes in three-dimensional space. They've drawn the planes in three-dimensional space. And in this case, you don't have three parallel planes, but you do have, you can just see that the planes will not all intersect in one point based on that figure. Okay. Okay, are there any questions at all? Who's feeling reasonably comfortable? Okay. Thank you, Haley. Thank you, Benjamin. Thank you, Nafoni. Eleanor, thank you. Lewis, thank you. All right, so you're feeling good. Okay, how many would like a little classwork time to begin working on their first homework, section 1.1? How many think, all right, I got a high, that's a positive response there. Yeah, so, it's sort of a natural time to take a little break. Our class goes to 8:45. Okay, so what I'd like to do is give you 15 or 20 minutes to work on section 1.1. So what I'm going to do is I'm going to stop the recording.